Welcome to Finite Element Analysis lectures by Civil Thinking, and this is our another class on Finite Element Method. Now before I move on, I suggest you to please watch the video lectures on Finite Element Method or Finite Element Analysis one by one as in the playlist so that you understand better. The playlist link is in the description, or also you can click on the pop-up on your screen. Now coming to the today's class. Now in this class we are going from bars to beams. Okay, now before I fully deep dive into the beams, it's better to give a comparative study between beams and bars, okay, so that we understand. Now this way it is going to be a bit of easy, a bit easier. So let us begin. Now as we know from the previous classes, what is a bar? A bar is something which carries an axial forces. All right, so if this is axis, if this is our axis, okay, so you can see we only have the axial forces, right? So because of this axial force, the this bar can elongate or it can compress, right? So there is only one deformation, and the deformation is along x-axis, right? Suppose this is x-axis and the deformation along x-axis is u, okay, so we have only one force present, okay, forces, and we have only u, only single displacements along the x-axis, right? Now when we talk about a beam, okay, so when we talk about a beam, okay, so this was bar, and let us talk about beam. Okay, now a beam, the major difference is right here, the force is along the centroidal axis, right? Now if you move this force, okay, if you rotate this force like this, okay, so that it becomes a transverse force, okay, then it is a beam. Okay, so the first basic difference is, in a bar we have axial forces, right? Axial forces. And in a beam we have transverse force, okay, transverse force, right? So what is transverse force? Transverse force is which is perpendicular, which is normal to the centroidal axis, the axis along the span of a beam, okay, or a bar. If the force is along this centroidal axis, it is a bar, and if the force is what, normal or perpendicular to the to the centroidal axis, then we call it as beam, right? So this is the basic difference we can say between a bar and a beam. Besides that, when we have transverse forces present in a beam, okay, then of course here it is going to be, there will be also bending moments. Okay, for example, if I take this point, okay, at some distance, then there will be a movement. For example, let us say that the distance is x, then movement is going to be this transverse force F, right, times x. Okay, now because of the movement, there is going to be also rotation, right? Rotation, because as you can see here, if I show it here, if this is a beam, it is if this is a fixed end, right, and we have this force and it is going to bend something like this. Okay, now you can see there is also a rotation, right, theta, right? So because of the forces, here it is also going to be a bending moment, right? Everywhere it is going to be moment. For example, at m1, here it is going to be this much of slope, right, theta 1. At m2, movement of m2, here it is going to be theta 2. Okay, so movement causes rotation, so these will be the additional number of what, unknown forces, okay, and unknown displacements. Okay, so now also because of this force, we will also have some transverse displacement, right? Let us call it as v. Okay, why v? Because it's along for example, let me show you here. If it is x-axis, it is y-axis, okay. So when it will, I have assumed the forces or displacements along this as u and the displacements along y axis as v, okay. So because right here it is the displacement along x axis, right, so it is u, and right here the displacement is vertical and vertical is y axis, so that is why I denoted it with v, okay. So we are going to have unknown forces, reaction forces, and the moments, okay. And what are going to be the displacements? Displacement is going to be v and theta, right? So let us move on. Now let us talk about stiffness matrix of each element in beam and bar, okay. Now if I talk about a bar or a rod, as I have told you in the previous classes, if this is a beam, bar, okay, here we have some force. If this is node 1 and this is node 2, okay, then what is going to be here? Because of this force, let us say the force here is F1 and the force here is F2. Here the displacement is going to be U1 and here the displacement is going to be U2, right? So the stiffness matrix of this bar element, right, because there can be multiple elements, but I am talking about single element of a bar, okay, then the stiffness matrix is K is equal to AE divided by L. Then we have minus 1, 1, 1 and minus 1, right? Or I think no, it is 1 minus 1, right? 1 minus 1, 1 and 1, okay. 1 minus 1 minus 1 and 1, okay. Now why they are, what is the this order of this matrix? It is number of rows is 1 and 2 cross, and number of columns are 1 and 2, okay, 2 cross 2, okay. Now why it is 2 cross 2? Because the total degree of freedom here is what? Here the degree of freedom is u1, here the degree of freedom is u2, okay. So total degree of freedom for this bar element is what? 1 and 2, right? So we have degree of freedom is 2, okay. And we know for a for a stiffness equation, the degree of the order is degree of freedom times degree of freedom, right? So this is the reason we have 2 cross 2. Why? Because each element have 1 and 2, total 2 degrees of freedom, so 2 times 2, okay. Now when I talk about a beam, okay, now in a beam we have transverse forces, okay. Let us say this is node 1 and this is node 2, okay. Now this is, let us say here the force is F1 and let us say here the force is F1 and let us say here the forces is F2, okay. Now because of these forces, here it is going to be some transverse displacement. If I show it like this with a red color, here it is going to be V1, right, here it is going to be V2, right. But remember, we are also going to have some moments, right? This is M2 and this is M1, right? And because of the moments, there is going to be rotations, right? So let us say the rotation here is theta 2 and let us say the rotation here is theta 1, okay. So how many are the degrees of freedom? Here at this node there can be a rotation and there can be a transverse displacement, okay. So here it is, at each node is 2, right? Here also there can be a vertical displacement because of the force, shear force, and there can be a rotational displacement because of the bending moment, right? So the total degree of freedom of this element is what? It is here for each node, because for an element the degree of freedom is the sum of the degree of freedom of nodes, okay. Here the degree of freedom is 2, here the degree of freedom is 2, right? So 2 plus 2 is 4, okay. So here the degree of freedom is 4. It means the stiffness matrix here is going to have an order of what? 4 cross 4. So what is the stiffness matrix for this bar is this, right? K equal to AE by L, 1 minus 1 minus 1 and 1, right? But what is the stiffness matrix of a beam element? It is a bit longer than this, okay? So it is better to remember, and I will simply paste it here, okay? So here we have the stiffness matrix of a beam, okay? So it is always, it is better to remember it, okay? Now there is also a derivation for this, and believe me, it is too much long, okay? So then you will end up like this, okay? Because this is universally for all kind of beams and all kind of loading. So I feel it is better to just simply remember this, okay? Stiffness matrix formula, okay? So here what is the order of this matrix? It is 4 cross 4, okay? So this is the stiffness matrix, okay? Remember, here the diagonalities, they are positive. Diagonal is always positive, and also here the diagonal is positive, right? All the values of the elements along the diagonal are positive, okay? Then also this is symmetric about the diagonal, okay? For example, here it is 6L, so it is going to be 6L2. Now here it is minus 12, it is minus 12, okay? Here it is 12 square, here it is 12 square, okay? Here it is minus 6L, and here it is minus 6L, okay? So you can see they are symmetric, right? This is 6L, this is 6L, this is 12 square, this is 12 square, okay? Minus 6L, minus 6L, okay? They are positive. Anyways, this, I don't think this should matter much, okay? Because you are going to remember as it is 12 6L minus 12 6L, 6L 4L square, okay? Then maybe you have to remember only half of this, okay? You can remember only half of this, okay? Because then other half is the mirror image, right? Because here it is minus 12, here it is also going to be minus 12, okay? Here it is minus 6L, here it is minus 6L, okay? Because because we have, it is symmetric about the it is a mirror image about the diagonal. So at least you can do is remember only the half, okay, of this, okay? So let us move on. Now let us talk about other other differences, basic differences, okay? And also we will summarize our today's class in this. Now degree of freedom per node for a rod, okay, rod or a bar, okay, is what? 1, right? It is for each node, okay? Now when we talk about degree of freedom of each element, what is it? It is sum of the degree of freedom of each node, right? So if I talk about an element, right, of a bar, okay, here the degree of freedom is 1, here the degree of freedom is 1, so total is 2, okay? So for this, degree of freedom of each element in a bar is what? 2, right? Now similarly, when I talk about a beam, okay, let us say this is node 1, okay, and this is node 2, okay? Now here the degree of freedom is what? Here it can be a displacement, for example V1, okay, and a what? A rotation at this node theta 1. Similarly here it is going to be transverse displacement of this node and a rotation of this node, okay? So here it is 2, here it is 2, and 2 plus 2 is 4, okay? So for each node we have 2, right? 1 and 2, and for the for the whole element, what do we have? What is the degree of freedom? It is 4, right? 2 plus 2, okay? Now matrix size of each element, what is the matrix size? Matrix size is, now for a load matrix, we know the let me write the the equation of stiffness. F is equal to K U, right? Now here the order of this force matrix is degree of freedom times 1, and for this stiffness, degree of freedom times degree of freedom. And for displacement matrix, okay, the order is degree of freedom times 1. Okay, I have also made a video lecture on this, you can watch that. Okay, and this is the reason I always suggest you to please watch my video lectures in sequence in the playlist. Okay, because in each lecture I say something. Okay, so if you follow the playlist, okay, that would be better for your understanding. Okay, so for a load matrix, this force matrix or load matrix, here the degree of freedom times 1 is the order. Okay, but what is the degree of freedom of this element? 2, right? 1 and 1 is 2. So load matrix order is going to be degree of freedom times 1, so it's going to be 2 cross 1. Now the stiffness matrix, what is the order? Degree of freedom times degree of freedom, right? It is 2, so it is going to be 2 cross 2. Now the displacement matrix, degree of freedom times 1. Okay, 2 cross 1. Now for a load matrix, again degree of freedom times 1, but degree of freedom is 4 here, so it is going to be 4 cross 1. Stiffness matrix, degree of freedom times degree of freedom, so it is 4 cross 4. And displacement matrix, what is the order? Degree of freedom times 1, so it is 4 cross 1. Okay, now what are the primary forces? The primary forces here, if we talk about this bar, right, so the primary forces are axial forces, right? So either they can compress it or they can expand it, so it is going to be either tension or compression. And as I told you before, in a beam we have bending moments, right? At any point we have a moment. Okay, and we also have shear force F. Okay, so bending moments and shear forces. Now the stiffness factor is EA by L. What is stiffness factor? It is what is outside the matrix of stiffness. This is the stiffness factor. Okay, here it is AE by L, but for a beam, what is the stiffness factor? It can be EI by L cube times 12, so it is EI by L cube. It can be also EI by L cube times 6L, so it is going to be EI by L cube times 6L. So L and this cube, one power will cancel. Okay, so let me show it here. It can be EI by L cube, right? When we multiply it by 12, so EI by L cube, because when something is outside a matrix, it gets multiplied to all the elements, right? So either it can be EI by L cube multiplied by 12, so what is going to be this factor? It is going to be EI by L cube. Okay, now when we multiply EI by L cube with 6L, right, then what is going to be? Now L, and here it is going to be square, right? So it is EI by L square. Okay, now we can also multiply by EI by L cube with 4L square, right? EI by L cube times 4L square. Then what is going to be the factor? Now here it is square and here it is cube. Okay, so it will cancel, so it is going to be EI by L. Okay, so the factors are EI by L, EI by L square, or EI by L cube. Okay, then when you multiply with others, so it is going to be either of these three. Okay, so this is the reason I have written here these stiffness factors can be EI by L cube, EI by L square, and EI by L. Okay, now what is E? E is the Young's modulus, I is the moment of inertia, and what is EI together? EI we call it as stiffness, right? Stiffness. Okay, or we also call it as flexural rigidity. Okay, now when we talk about the forces, here the forces are always axial, right? Equal and opposite axial forces. And when we talk about here we can have shear force, right? We can have bending moment. Okay, so this is the reason we talk about shear force diagram. Okay, shear force diagram and bending moment diagram. Okay, so because we have shear forces and bending moments, we often draw what? Shear force diagrams and bending moment diagram of beams. And but when we have the bars, we often draw what? Axial force diagrams. Okay, so shear and bending, okay, are the forces here, primary forces. Now where it is applicable, you know, the bar, this when we talk about a truss, okay, so each element, okay, is a bar, okay, or a rod, okay. Now similarly the rods, okay, because bar and rod, okay, they are kind of same thing, okay. Now when we talk about this beams, now where it is applicable, it can be applicable in beams or, you know, frames, okay. The frames, because in each frame when you have the loading, okay, this is, we are going to have bending moment and shear forces, okay. So we are going to analyze it like beams, okay. Each element of a, you know, frame can be treated like a beam, okay. So basically wherever there is bending moment, okay, so it is going to be it can be analyzed like a kind of beam, okay. So this is the reason I have written bending dominated, okay, structures, okay. So I hope you understand everything, okay. But as again, please remember this formula, okay, because we are going to solve problems on this, okay. So that's it for today. If you have any doubts, you can comment or you can contact me. So see you in the next class. Thank you.